Okay, people, welcome back. So we are looking at analysis of reactions involving reactive species. And for the analysis of free radical reactions, we said that this is a nice framework. It helps us with a pseudo steady state assumption later and so on and so forth. We may look at it at some point in time, maybe as a part of our work. We had used a pseudo steady state to come up with some models. So we'll look at that point in time. For now, you could look at free radical reactions as initiation reactions, propagation, termination. So we look at this, and then of course the reactive species that are not free radical, you could look at them from a regular perspective, include them as a part of these reactions, which we actually did. And when you do genome scale models, it doesn't really matter. You can do the whole thing, but you need to take care of the other aspects. Probably we'll touch upon that towards the end. The work just got over. The paper was published a few months ago. So, a big piece of work. We'll talk about that. I need to prepare for it and we'll talk about it. Okay, fine. So, yeah, note that only some reactive species are free radicals, others are not. We've already seen examples of both. So, let us start with some initiation reactions. The whole idea of this is to introduce you to some free radical reactions which are popular, which you see happening all the time, which somehow seem to be important. And more the merrier, where we don't even attempt to cover all reactions. We just cannot. We just look at some popular ones. Okay. The first one we are going to look at is called the Fenton reaction. Does anybody who does not work in reactive species know what a Fenton reaction is? Recall what a Fenton reaction is? You've definitely heard the name earlier, you would have forgotten, that's okay. Fenton oxidation. But yeah, exactly. Papers there. So do you recall the reaction? But you work on reactive species, so that's an unfair advantage that you have. So I'll keep blocking off people who have ready-made answers and so on and so forth, so that the others have a fighting chance. Anybody else that? Okay. As Ankita rightly said, it is a reaction that is a well-known reaction to generate hydroxyl radicals. We'll start from there. And it involves the reaction between hydrogen peroxide and metal ions such as iron, copper, and other species. Let me say that. Okay. So let's start with iron or copper. Iron is the most well-known. Ferrous reacting with hydrogen peroxide is the most well-known. However, other equivalent reactions are also called Fenton reactions. The reaction between hydrogen peroxide and iron is, as Ankita explained, hydrogen peroxide plus ferrous giving you a ferric. There is an oxidation of iron, and there is a reduction of hydrogen peroxide to give you hydroxyl radicals, and there is an hydroxide ion also that comes along with it. Okay, note that there is a difference between hydroxide. Of course, they're totally different species. You just cannot compare. Hydroxide is what you're most comfortable with in the context of acids and bases and so on and so forth, but that is very different from the hydroxyl radical. Hydroxyl radical is a free radical which has an unpaired electron and highly reactive, much more reactive than the hydroxide ion. Any questions? Despite its popularity, if you look at the second order reaction rate constant of this particular reaction, it is only 76 per molar per second. Okay. Whereas we think in terms of 10 power 8, 10 power 9, 10 power 11. I have even seen 10 power 11 at times with hydroxyl radicals. That is, and reactive species are usually reactive and so on and so forth. This is one main reaction why we cannot really define reactive species as highly reactive. Okay, the speed is very low. Okay, 76 per molar per second is not much at all. Okay. But it's a very important reaction. It's considered there's a hydrogen peroxide here, there's a hydroxyl radical here. What more do you want to call it a reactive species? Okay. And of course, as mentioned, the reaction between hydrogen peroxide and cuprous to give you Cu plus to give you Cu2 plus, cuprous cupric, also is called the Fenton reaction. But for molecular reasons, the rate constant, the second order rate constant, is many orders of magnitude higher. It's about 3 orders of magnitude higher, 1000-fold higher almost, or 500-fold higher, whatever you want, 600-fold higher. Okay. Some variants of the above reaction is also called, or are also called, Fenton reactions. Okay. We will see some in the context of a problem. For example, the reaction between iron ATP, okay, it's a complex ferrous ATP, or ferrous citrate and hydrogen peroxide, is also called the Fenton's reaction. And this reaction is far more common in the cell than probably, even iron and copper are quite common, because iron is present in any tap water, copper is also present. Any groundwater will have some amount of copper, a lot of iron, and so on and so forth. In the cell, iron gets chelated to citrate to give you iron citrate, ferrous citrate, or it gets chelated to ATP to give you ferrous ATP and other molecules. The rate constant for the chelate with hydrogen peroxide is much higher than that of iron. Okay. For example, it is 1.6 into 10 power 4, more than the one with iron, much more than the one with iron, or more than the one with copper at 37 degrees C for the ATP chelate. And again, of the same order for even the citrate chelate, and this is an estimated value. It's not measured, at least from the source that I have taken it. This is a compiled source. At that point in time, till 2015, it was not measured properly, that is. And in normal physiology in the cell, typical intercellular concentrations of hydrogen peroxide is about 10 power minus 8 molar. Under standard conditions, there would be variations, but under standard conditions, about 10 power minus 8 molar. It's good to note this down, remember this, 10 power minus 8 molar. Ferrous citrate happens to be 10 power minus 6 molar, typical value, and of course, they are very low. Okay, so let's get a little more comfortable with all these concepts. Estimate the number of hydroxyl molecules produced per second per cell due to a Fenton reaction under the above typical conditions. Above typical conditions are these. Okay, I hope you have written these numbers down. Okay, so with these numbers, estimate the number of hydroxyl molecules produced per second per cell. That should be quite eye opening. Can you do that? Take about 5 to 10 minutes, and I'll finish attendance by then. Yep, it's been about 7-8 minutes. All done. Any answers? That's okay. Yeah, here you are. Oh my goodness. I hope you had come a little early. Anyway, it's okay. I'll mark in my thing. Unfortunately, I uploaded the. I was talking. I think he's busy. Uploaded the formal attendance a minute ago, so you won't get it. So, but I'll mark in my records. turn red. Okay. Okay, any numbers? Order of magnitude? It's per second per cell. Okay, and you know how nasty hydroxyl can be, right? It pretty much reacts with everything very quickly. Okay, let's look at a solution. We could have arrived at this through many ways. So, according to the definition of the rate, it's rate constant times the concentration of hydrogen peroxide and ferrous citrate, in this case second order rate constant. So, which happens to be 1.2 into 10 power 4, right? The numbers given. Hydrogen peroxide concentration in the cell 10 power minus 8, ferrous citrate concentration 10 power minus 6, and therefore the rate is this much, 1.2 into 10 power minus 10 per molar per second or moles per liter per second. Okay, but this appears small, 10 power minus 10 in terms of the rate. Okay, but don't be seduced by that. Let's calculate the number of hydroxyl molecules formed per second, which is what has been asked in the problem. So, 1.2 into 10 power minus 10 molar per second is so many molecules per second. You have an Avogadro, I mean, a mole contains an Avogadro number of molecules. Therefore, you multiply it by the Avogadro number 6.023 into 10 power 23 to convert it into molecules per liter per second. So, this number happens to be 7.2 into 10 power 13 molecules per liter per second. Okay. So, far so good. And that is not all, we want per second per cell, right. So, we have molecules per liter per cell, sorry, per second, right. So, we need to get rid of this and the way to get rid of this is by multiplying it by the cellular volume. So, for cellular volume we start making estimates, we are doing engineering. So, we start making estimates. So, a typical mammalian cell diameter is of the order of 10 microns. You won't be very wrong if you choose this in most cases. Nerve cells are bigger, of course, many times bigger, but 10 microns is a good typical size. So, the volume is of the order of 10 power minus 15 meter cubed or 10 power minus 12 liters, right. Pi d cube by 6. So, diameter is 10 into 10 power minus 6 meters. So, 10 power minus 5 meters. So, pi into 10 power minus 5 cubed. So, you will 10 power of the order of 10 power minus 15, which is 10 power minus 12 liters. Therefore, you have 7.2 into 10 power 13 molecules per liter per second, giving you each cell is 10 power minus 12 liters, and therefore 72 molecules per second per cell. Okay, that's a huge rate. If you think in terms of hydroxyl, its destructive power, its oxidative power within one single cell per every second. Okay, so that is what this is capable of, and that's the insight that you get by doing analyses of this kind. Any questions or comments? Hmm? No. Those are typical values. They vary, quite significantly at times. Of course, there's a certain range in which they vary for homeostatic conditions. When it is when it's a pathological condition, non-homeostatic, it can vary hugely and so on. My PhD work was in the area of intracellular pH. Okay, many years ago. So, we were looking at bioreactors at that point in time, very popular. So, we wanted to understand the culture. So, because the cells are the actual factories that produce the product. So, at that one set of efforts were towards understanding the culture a lot better, even through soft means. Okay, redox ratio was popular at that time. I mean, that's kind of a soft measure, NADH by NADH plus NAD and so on and so forth. So that you could relate to various things, and then you could relate to some biochemistry and so on and so forth. There was no holistic way of looking at things formally at that time in the mainstream. People had started looking at reactions and so on and so forth from a holistic point of view from the 70s onwards, but it had not crept into the mainstream till then. This is late 80s. And yeah, we were looking at intracellular pH as an indicator of the metabolic state of the cell. The idea was my advisor's. He felt that he was very caught up with Mitchell's hypothesis. Mitchell, if you recall Mitchell's hypothesis, Mitchell won the Nobel Prize for this hypothesis. Before that, people knew that there was ATP production in the mitochondria. They were trying to figure out an intermediate which provides the energy for ATP synthesis. Okay, they could never find an intermediate until Mitchell came in 1966 or something like that. He came up with this daring idea that the difference in the hydrogen ion concentration between the matrix of the mitochondria and actually he thought about an integral membrane. That's all. We apply it to mitochondria, we could apply it to the cell also, as long as there's an integral membrane. If you have a difference in hydrogen ion concentrations across an integral membrane, there is enough potential to generate ATP. That is, in some words, not exactly his hypothesis, in some words. He won the Nobel Prize for it because he found out the missing intermediate that provides the energy for ATP synthesis. So my advisor was quite caught up with it. He felt that if he can somehow find the intracellular pH, the energy status of the cell, and thereby get some fuzzy picture of what's happening to the metabolic state. All these are soft terms of the cell. Okay. And so mine was the first work in that area. So we were trying to measure the intracellular pH continuously in a bioreactor. So there would be cells. We use some method by which we could measure intracellular pH. Okay. At some other point in time, I'll tell you that story. But for now, the reason I thought of that was the intracellular pH remains reasonably constant at around 7.4 for mammalian cells, and it's quite narrow. You get to 6.8, the cells are dead. You get to 7 point plus something, 7.6, 7.8, the cells are gone. So it's a very narrow range for homeostatic existence. However, when there are processes, big processes happening in the cell, when it goes into hibernation, the intracellular pH can change by 1 unit, and so on and so forth. So certain cells, not mammalian cells, not these mammalian cells that we were looking at. And when the cell division happens, it goes up by about 0.6 units or something like that. So there could be a wide range, even in things that are quite tightly regulated. So yeah, to answer your question, yes, we are talking of some values which are typical values. They usually are within a certain range for most cases, but sometimes they could vary quite drastically. Any other questions? So this is of course substantial enough to cause damage and so on and so forth. Okay, so that is with Fenton reaction. Ion chelates can react with hypochlorous acid, HCl is hypochlorous acid, to produce hydroxyl radicals. Okay. If you have, I'm sure I mentioned this, all these are initiation reactions. We are looking at formation of free radicals for the first time. If you look at the left hand side, there will be left hand side of these reactions, there will be no free radicals. The right hand side would have free radicals, as simple as that. So you have iron chelate plus hypochlorous acid giving you ferric chelate plus a chloride ion and a hydroxyl radical. Okay, this is a typical reaction. The rate constant happens to be 10 power 4. Keep noting the magnitudes so that you'll have an idea of the reaction. I don't expect you to remember any of this, and of course, there's no what shall I say, testing process in this entire course to check any of this. Whenever you need, you can go and refer to the books and get these numbers, or refer to databases. NIST database is a very good database, and get these numbers. In fact, when we try to put all these equations together for a metabolic model, I felt the work would get done in 2 years, because we have this NIST database which has all these things and so on. It took 5 years, because whatever came from NIST database was fine, but it was not complete enough for our use. We had to balance charges, we had to balance masses, we had to balance everything, and so on. So students had to do it, of course, and that was quite a messy thing to do. We'll get to that towards the end of the course. Hypochlorous acid is used to disinfect water. If you already didn't know, common knowledge, it is actually bleach. Bleach is sodium hypochlorite, which produces HCl on reaction with water. Bleach is a powder, so it's easy to transport and so on. It produces hypochlorous acid on reaction with water. And please go to your Moodle page and watch these 2 videos. This is a tongue-in-cheek video. This is how you spin your research to connect with the public. This is how you need to spin your product to connect with the public if you're into startups and so on and so forth. Okay, which is very different from a purely academic viewpoint, but these are necessary to have, right? It's a good time that you picked up these. So please watch this a few minutes, I think, each, and then we will continue. Madhav, you have access to Moodle, right? Yeah. Does anybody not have access to Moodle? You have access to Moodle. Okay, then I think everybody has access. Okay, that was just to make a point that when you do startups and so on and so forth, you need to think of giving it so much of a spin, call HOCl Hochul and so on and so forth. Only then will it sell. Okay. That's how we scientists are a rarefied group. The general public will relate only to Hochul. It will not relate to HOCl. But this is a fact, right? There's nothing odd about it. So you need to change your approach to be a successful startup. Okay. Which academics take a long time to realize. Okay. Any questions, comments? What are we doing in terms of time? Yeah, we have time. And this also provides a good distraction from reaction. So, the first time I taught it, how would I go about improving this? I mean, you need to know about these reactions. There's no way out of it. But then I slowly realized I could do this. Then I think in 2017 or 2018, we started doing some games to reinforce certain things. We'll also do that. Your TA will take care of those games. If you've done the transport course, you know some games. We'll have slightly different games here. Okay. Yeah.
HOCl also reacts with the water to release blockage.
Yes, certainly. Yeah. It's bleach. It's HOCl reacts with many things. So sodium hypochlorite reacts with water to form hypochlorous acid, and hypochlorous acid is the one that creates all these oxidations, and it's a nasty material, but it's very useful, and very useful as you saw in the videos and so on. So certainly, yes. Any other comments, please? Okay. So photolysis, yeah, I showed this breakage of bonds using light. Okay, it could be any wavelength, typically UV, and other wavelengths are used to break bonds of molecules, appropriate molecules. Photolysis usually results in equal fission of a covalent bond or a homolytic fission of a covalent bond. Okay, one electron gets taken up by one part of the molecule, the other electron gets taken up by the other part of the molecule. That's what equal fission is, or homolytic fission is, homolysis. Yeah, each species takes an unpaired electron to result in a free radical. For example, UV induced homolytic fission of the OO bond in H2O2 produces hydroxyl radicals, right. So, there is OO bond, if it is broken by UV, then you get hydroxyl radicals, and that is the basis for a lot of environmentally useful treatments. It is UV based decomposition of waste, organic waste using hydrogen peroxide, well known technique, a lot of work is available on that. So, this is what happens, you have OH, you put in a UV, you get two hydroxyl radicals, and this is actually what does the treatment. Note that in the cell, hydrogen peroxide is produced as a part of the normal metabolic processes. We have already seen it, a set of basic reactions involving oxygen, a 2 electron reduction results in hydrogen peroxide, right. So, oxygen superoxide, hydrogen peroxide, hydroxyl and water. 4 electron reduction gives you water, 2 electron reduction gives you hydrogen peroxide, and hydrogen peroxide is produced as a part of the normal metabolic processes in the cell. Many enzymes such as xanthine oxidase, urate, SOD is superoxide dismutase, and others also generate hydrogen peroxide. Some other RS reactions also generate hydrogen peroxide, and these reactions could be relevant in aspects related to skin aging. If the skin is exposed too long to sunlight, UV rays in it can penetrate the skin into the skin cells, generate hydroxyl radicals by homolytic fission that we saw earlier, and cause cell damage, especially DNA damage. Okay. Once you get into DNA damage, cancer and things like that arise. It can cause skin cancer, called basal cell carcinoma or malignant melanoma. Okay. Highly fancy names, different types of cancer. Of course, they all have a basis and so on and so forth, right. But yeah, these are the various terms: carcinoma, melanoma, basal cell carcinoma, malignant melanoma, and so on. So, we will close with this. Please watch these two videos. You can start watching it now, and then I will walk out in a few minutes time. I mean, about 4 minutes left, I will walk out then. You can continue watching it, or you can watch it at home, outside the class. Okay. So, this is videos on what does sun exactly do to your skin, what causes sunburn. Okay. Take a look at this. All due to photolysis, a homolytic fission of hydrogen peroxide due to photolysis. Go ahead, please.